Hello everyone, welcome to another deep learning session. Today we are having our second meetup on GANs. We're so happy to have André Carreiro as our speaker today. André is a senior scientist at Fraunhofer, and today he's going to talk to us about CycleGANs and some friends. As usual, our guest speaker is going to present his work for about 45 minutes, and then we'll have about 15 minutes. Hello everyone, welcome to another deep learning session. Today we are having our, we'll have 15 minutes reserved for Q&A. So please, we encourage you to leave your messages and comments or questions in the YouTube chat so we can collect them and ask them in the end. André, it's a pleasure to have you here and thank you so much for accepting our invitation. I'll hand over to you now.
Hello. First of all, thank you for inviting me here. It's a real pleasure to come and talk about this interesting world of GANs. I know that Fabiana Clemente has already had a session before, an introduction to these generative adversarial networks. And today we're going to dive a bit more into CycleGANs and some variations. So I can start my presentation. I don't know if you can share it, okay? So the title is Transforming Reality with CycleGANs. I put it in parentheses because I'm not going to just talk about CycleGANs, but other variations as well. And with this type of networks, we can really transform reality, and we will see how. So just to give an outline of the presentation, I will briefly introduce myself and Fraunhofer Portugal. Then I'll do a brief recap on GANs, because I'm not sure if everyone attended the previous session. Then we're going to dive deeper into image translation, presenting a bit on CycleGAN and friends. Then I'm going to show you a bit of our work using GANs at Fraunhofer Portugal, mainly focusing on two use cases relating to dermatological lesions and the analysis of retinal images. And finally, if we have the time, I'm going to go through a quick tutorial that is available, and then you can explore later on if you want by yourself. Okay, so I'm André Carreiro. I'm a senior scientist at the Intelligent Systems Group of Fraunhofer AICOS. I mainly work with computer vision and multimodal AI, so integrating different sorts of data. But my main focus has been on deep learning. I have a PhD in biomedical engineering, which is also the area of my master's in Technical. And since my master's, I've been applying data science in healthcare, and my PhD is exactly just that. So doing data mining in an integrative way, combining different sorts of data and applying it to ALS, which is a neurodegenerative disease. Then I got a bit disappointed with the academia, and then I joined a startup. The first one was I was working as a developer of machine learning layers of a full stack for data science. So the full stack comprised from the database to ML layers and applications with front ends. Then I switched to another startup where I was for 2 years, working on applying deep learning for human behavior analysis from video data. Then I joined Fraunhofer early 2019, so almost 2 years in a few months. And just to introduce you a bit about Fraunhofer Portugal, so we are part of one of the largest applied research groups in Europe, which is Fraunhofer Gesellschaft. I'm not sure if you ever heard of Fraunhofer, but if you heard of MP3 format, it was invented by an institute of Fraunhofer. This research group has many different institutes throughout the world. Actually, the Portuguese Fraunhofer Portugal was one of the first research centers outside Germany, and we are proudly in business for 11 years now. Okay, so just to give you a context on why Fraunhofer Portugal is a bit different than other R&D institutions in Portugal. So our funding is mainly broken into 3 ways. So we have base funding from Fraunhofer Gesellschaft in Germany and from the Portuguese government. Then we have a third of funding, which is that we get from national and international programs like Horizon and such. And then the final third is directly contracted with industry clients and partners. And if we don't get this third, we don't get the other ones. And so this makes us really focused on replying to the market needs. And so we have to make sure that our research is translated into the industry, into practice. Okay, so we have three different groups at Fraunhofer: intelligent systems, where I'm part of, and we work with computer vision for edge and cloud. We work with embedded intelligence in embedded devices, deep learning, predictive modeling, and whatnot. Then we have a group of connected things, which is more low level and works with the sensorization, the actual embedding in electronics, quality assurance, and stuff like this. And finally, because we cannot forget about people, we have a group of human-centered design. Already we understand people, their needs, how they interact with the products, including AI-based products. And so, for example, explainability is also a concern of ours when working with AI. Okay, so this just to finalize a brief summary of Fraunhofer, we have different areas of portfolio. And today I'm going to talk application of GANs in two of them, in Derma and Ophtha, although we also apply it in Micron, for example. Okay, moving on. So a brief recap on GANs. So I agree with Ian LeCun that in 16 said that adversarial training is really the coolest thing to happen in the last decades in machine learning. Although this approach of adversarial learning is recent in 2014, introduced by Ian Goodfellow, it has really boomed in the literature. And as the name suggests, we are really just putting two networks against each other in a sort of a game. The idea is that these networks can learn to mimic any distribution of data. This can be speech, images that we are going to talk about today, but can also be text, tabular data, as Fabiano mentioned in the previous session, even music. And regarding art, I brought here an example of a GAN-generated painting of sorts that was auctioned for over $400,000. And this has actually an interesting story behind it, because some guy is suing the sellers because they say, and of course I'm biased because I agree with him, because he says that the seller stole his code from GitHub. So if you're doing really cool stuff with GANs, be sure to somehow protect it, or at least make it clear that it's your own work. Okay, so diving a bit deeper into the scheme of a GAN, we have a generator and a discriminator. So these are both the networks that we're going to pit against each other. And so the generator takes random noise as input and can generate a fake sample of a given domain. And then the discriminator looks at fake samples and real samples and will try to distinguish them by classifying, by outputting a probability that the sample is fake or real. And then we use backpropagation to train the whole loop. So the idea is that this is a zero-sum game. And so we want to maximize, the discriminator wants to maximize its accuracy, both in real and fake samples. Otherwise, on the other hand, we have the generator that wants to fool the discriminator. And so he wants to minimize this accuracy. Okay, this is a bit of math. I'm not going into much detail on the math. And so I really like to using a different analogy for explaining again. So think of someone who's counterfeiting dollar bills and someone who is like a police force that is tasked with finding the fake bills and distinguishing fake from real ones. And so initially, a few years back, the quality of the generated bills was not so good. It was easily distinguishable. But as they go back and forth, and nowadays, these forgers of dollar bills are getting so good that the methods of distinguishing have to keep up. And so they have also to improve themselves. And we can also make different analogies like this. For example, in cybersecurity, if you think of hackers and white hat hackers that are supposed to protect us, they are also on this rat race that one side improves things and so the other side has to keep up. And so this is, when we talk in the min-max game, we are talking usually on things like this. Okay, moving on. So GANs can be used, as the name suggests, for generation. And so one of the first applications that, and one of the most common, is to generate samples from a given distribution. And so here on the left, you can see, I'm not sure if you can see it very well, but these are fake bedrooms that are generated from random noise. On the right, you have fake faces. Actually, these ones are based on celebrities, so you might see some resemblance of known personalities as such. But you have also some interesting websites, like I think Fabian also mentioned it, like thispersondoesnotexist.com. If you go to that website and you hit refresh, you'll get a new face every time, which actually doesn't exist. GANs can also be used for image translation or styling images in change domains. And I dare you to open Artbreeder after this presentation, to open Artbreeder and explore by yourself. Actually, they don't use CycleGANs behind it; they use big GANs. But the idea is also to do image translation and combination. And so interesting applications of image translation are, for example, you can, and I saw a video from NVIDIA where they can draw here, and I'm not sure if, okay, you can see the mouse. You can draw here something, call it, okay, blue is car, purple is road, and then you hit generate, and it generates a real image from this. Or you have an aerial image and it generates the map, or from a set of edges, it generates a real image, or colorizing images. You can do all sorts of things, and imagination is really the limit. Of course, we have here the classic, for those of you that have read the CycleGAN, the classic example is turning zebras into horses and horses into zebras. But you can also apply change photographs like summer to winter, day to night, whatever comes to mind. So changing different domains. But since GANs can learn virtually any kind of distribution of data, you can use it to learn a normality distribution. And so you can also use GANs for detecting anomalies. And ANOGAN, which is now a recent version with fast ANOGAN, is actually used for this purpose. And so they use a GAN and an encoder to learn what is normal, for example, for tissue data. I'm not sure if this is MRI or CT scans, but they learn what is normal for the tissue, and then when they get unseen data, they can target and actually color the anomalous pixels that they find. Okay, and this actually improved the state of the art in anomaly detection for several different problems. Moreover, if we try to learn this underlying distribution in a latent representation using an encoder, we can also learn to perform clustering in a better way that we used to work with before. And so so here we have the generator in green, the discriminated in yellow, and what they did was adding an encoder so that they had a latent representation. I'm not going into much detail, just want you to know that it's possible to perform clustering using GANs. And actually ClusterGAN has a particular advantage, which is because of this smooth latent representation in space, you can actually tune how to transfer between clusters, and you can smoothly change from one cluster to the other. So it can smoothly change from in different digits. For example, here you see the 2-digit turning into a 1. You can here see a long jacket turning into a pantsuit and then to pants. It's very smooth, and this has very interesting applications. Okay, so now diving deeper into image translation. So one of the first models was Pix2Pix, and for those of you that are familiar with image translation, you've certainly heard of this in 2017, early in the year. And so this is an example of a conditional GAN, because it learns image-to-image mappings under a set of conditions, as opposed to the classical or vanilla GAN, which generates from a random noise with no conditions. But the problem with this approach is that you have to give a pair of input and output. If you are working here in the example with edges and real images, you have to provide for each example the corresponding edges in real images. Okay, and so for this example, he uses the edges to generate real images, and then the discriminator only has to discriminate which is real, which are the edges that are really generating this photo. And just to add a bit of math here, so we have the adversarial loss as before, and they also add an L1 loss, just to assure that the real image corresponds to the real output. Okay. Another interesting thing about this paper is that they introduced a specific type of discriminator, which they called as patch GAN, and it's nowadays one of the most used types of discriminator, that instead of looking at the whole picture as a whole to decide if it's real or fake, it goes around each patch n by n pixels and traverses the image, and for each patch it has a decision on the local structure if it's real or not. And so this can be thought of as a type of a loss that penalizes local structure, and so we can think of it as a texture or style loss. Okay, so these are the actual applications. Some of them we have seen before. Just here another example of using labels to draw buildings. And so the generation is really realistic. Okay. And for example, you can improve things, for example, thermal imaging into real world, into real pictures. And an interesting thing is that although the model learns with real edges, for example, using an edge detector, they found that if you draw them by hand, which is not very good, it still provides you realistic outputs. And you have an online tool, which then I can give you the link, that you can draw cats and it will generate. And some of the things that the model outputs are really incredible on both sides, on good and bad. But I'll leave you to that. Okay, so now reaching CycleGANs, which is from the same group, but a little later, so a few months later. Unlike Pix2Pix, here he doesn't require pairings of images. So it doesn't require the real X and Y input-output pairs. And so they call this unpaired training. And the only thing you need is two sets of domains, two sets of pictures or images for each domain, okay? So to go away from the tired example of horses and zebras, let's imagine we wanted to build a Simpsonifier. And so we want to turn photos, real photos, into characters from The Simpsons. And in the other way around, because it's the CycleGAN, we could also turn Simpsons into real people. Okay, so in CycleGAN, we need two generators and two discriminators. We need one generator, G, to transform photos into Simpsons, and the other way around, another generator to transform Simpsons into real photos. It's G and F. And so we also need two discriminators, one that can discriminate real from fake photos, and the other one that can discriminate real and fake Simpsons. Okay, with this in mind, okay, just preparing you for some math, but I'm not going to go too much into it, but I figure it's better to leave it here on the slides if you want to check them out later. So just the main idea, you have an adversarial loss or GAN loss as before, which is the min-max game we were playing. And so we have, the first thing is using the generator to generate Simpsons from real photos, okay? And then we have in the other direction, the other generator generating real photos from Simpsons. And this is the loss. So this loss ensures that what we are generating is a realistic Simpson, or on the other hand, a realistic photo. Okay, this is what this loss term handles. Then we have a cycle consistency loss. And here is the magic of the CycleGAN that ensures better reconstruction, and this allows us to preserve key features from the domain. And so the idea is that since we have a transformation from real photo into Simpson, we should be able to map again into the previous domain. So we should be able to retrieve the same picture if we used generate F again on the created Simpson. And on the other direction, we generated a real photo from a fake photo from a real Simpson, and now we should retrieve back the real Simpson. And so the idea is this one, that we have a forward consistency loss, that we go from X to Y and back to X, and we want this distance here, this space here to be as close as possible. And the same for the other direction, which is called backward cycle consistency loss. And so we have to include this term in our global loss. Finally, and this is an optional loss term, but the authors find that if you want to preserve things like colors or textures from the original domain, this identity loss really helps, as you can see on the figure in the right. Okay, so the idea with identity loss is very simple. It's just expected that if a real domain image is passed through the corresponding generator, it's still preserved. So if you pass a Simpson through a Simpson generator, the result should be similar to the input, okay, because it's already a Simpson. Okay, so the final loss is just adding all of these terms and minimizing it, such as you would do in any other kind of network. So these are just examples of the results in the CycleGAN and how each component helps. So in the first column we have the input, then we have using just the cycle consistency or just the GAN loss, the adversarial loss alone. Then using GAN plus the forward consistency or GAN plus the backward consistency, and then the whole thing. And we can see that every one of them has its contribution to achieve a better result. Okay, moving on. So these are, okay, I moved away, but not so much. So these are the results from the paper, successfully translating horses into zebras and zebras into horses. Of course, it's not perfect, but it has impressive results. We can also turn winter images into summer, summer into winter. And this is especially important, for example, if you're working with self-driving cars or self-driving algorithms to install in self-driving cars. This is a really good way to perform data augmentation in scenarios that, for example, in Portugal, if you were just to collect data in Portugal, we have smaller sites where it actually snows. And so having techniques like this really helps in improving the models. Okay, limitations of the CycleGAN. So the first of all, if you are changing domains that have structural changes, CycleGAN can struggle with this. For example, turning dogs into cats, and so the output may not really work. And the other thing is that CycleGAN does not generalize well outside what it sees in the training, and this is actually true for every kind of network. For example, in the horses dataset, there were no riders, and so when they gave this image as input, the output also turned Putin into a zebra. Please don't show this in Russia. But just to show that CycleGAN is not perfect. Okay, then in the same year, we have another working group that proposed non-supervised image-to-image translation networks, which is called UNIT, which instead of having an explicit consistency loss, they map both domains into a shared latent space using an encoder. And so we have GANs for the generators and we have variational autoencoders to map the domains into a shared or common latent space. And so here, if we recall the photos in The Simpsons, we have the domain x1 of photos and domain x2 of Simpsons. And the idea is that the encoders E1 and E2 would map these things into a shared Z space. Okay, so just to explain it a bit visually, we have two paths here with the common Z, or the common space, and then we could input an image through X1 and reconstruct it using the path in above, or providing a Simpson and reconstruct it using the path below. But we can cross paths here, and for example, using X1 as a real photo, we can use the generator to generate a fake Simpson, or the other way around. We can give it a real Simpson and generate a fake photo if we cross paths. So it's not really that complicated if we think of it in this way, but it has some interesting properties. These are some of the results they obtained in the paper. For example, transforming an input dog into different breeds, because it learns to cross path the different domains. And this really works because the changes are in textures and small traces and not really big structural changes. Of course, we can also do this as you may know, the Face app and the snapshot filters and so on. They use stuff like this to turn your hair blonde, to make you smile, to apply beards, to make you change gender, and stuff like this. They use these kind of networks. Okay, now we have a recent paper that it's from August in this year. And this is really cool because it uses contrastive learning and it allows for one-sided translation. So until now, using CycleGANs and UNIT, you always have both directions. If you wanted a Simpsonifier, you would always get the other way around, the personifier for Simpsons. Okay. In this case, you get just one-sided translation, so it bypasses the cycle consistency. And the idea is to use this contrastive learning using positive and negative examples of patches in the images and maximize the mutual information between the corresponding input and output patches. Here in the right, let me just restart these images. And so you get a patch from the output, you match the input, you get negatives from the same image, and then you get probabilities which correlate with the mutual information. And because you are sampling negatives from the same image, you don't need many images or a big data set in each domain. You can use translation with a single image, which is very interesting for people that are working on these types of techniques. So this model actually has reduced complexities and training times when compared to CycleGANs. And so I haven't tried it yet in practice, but I'm eager to do so. And the idea is that the generator is broken into two components. So we have a component that is an encoder and a decoder. And similarly to UNIT, and this is why I mentioned UNIT before, it also uses a latent space, and this is why we have an encoder. And so what he does, it encodes the features, and then he has some dense layers, which is called here H, which is just an MLP, to build a feature map for the output and the corresponding patches, positive and negatives, in the input, and then compute similarities and performs n-way n+1 and negatives and the positive n+1 way classification using cross entropy. And the idea is that, okay, mentioning here the loss terms, we have an adversarial loss, a GAN loss, as before, is very similar to before. Then we have the cross-entropy loss, which is also standard for every framework, which is the final classification I was showing here before, then in the final vector here, okay? And the idea of this cross-entropy loss is to give you the probability that a positive example is selected over the negatives, okay? Because we want this matching of input and output. We want, for example, in this case, that if he's choosing the face, it should be similar to the face of the input, or a leg should be more closely resemble, a zebra leg should closely resemble a horse's leg in many properties, okay? Then we have a patch NSE loss, which is more specific to this kind of model, which I'm not going into detail. It just uses for each layer that you consider in the network. It also considers the spatial location of the patches and uses a summed loss over all of these patches. Adding all up, you have the final loss. It allows you to train the network more efficiently than you do so with the CycleGAN. Okay, these are some of the results comparing with the CycleGAN. And so we see that in cases that the CycleGAN image was not so realistically in the target domain, and this cut actually improves the results, and especially for single image translation. So given a single image domain here, the smaller one here in the corner, they apply single cut, which is this one, which compared to other ones, it's actually has better results without having a real big data set to train on. Okay, this concludes the theoretical part. Now I'm gonna explore a bit of the work we've been doing at Fraunhofer Portugal so far using GANs. So not just cats, zebras, and Simpsons anymore. So the first one has to do with dermatological diagnosis, which is actually part of our portfolio. And this work was performed by Catarina Andrade and my colleagues at Fraunhofer during her master's thesis. And she continues to work with us and with GANs, actually, to this date. So our main goal is to turn teledermatology a reality, which is especially important nowadays with the pandemic situation. And one of our problems that we want to solve is to segment skin lesion or moles using a simple smartphone camera, which is called macroscopic images. However, there are little annotated data sets in this macroscopic domain, even though we have some available in the dermoscopic domain, which is this little device that dermatologists can record pictures with. I'm going to show you a bit. Dermoscopic images look like this, and we can see the structures and features. It has a flat outward aspect, so it really flattens the image. It has this sort of glow about it. In contrast, we have macroscopic images that we can have a surface glare. It's typical to have a surface glare. We have a more depth perception on the lesion. We also have decreased resolution. But this is the kind of images we want to work with if you want to apply this to a smartphone camera and allow, for example, non-specialists to do triage at local centers. So the idea for a thesis was to learn to segment lesions using the dermoscopic, the available dermoscopic data sets, and she used UNet and DeepLab with the mobile net encoders, just to mention. And then was to find out if she could use CycleGAN to map from dermoscopic to macroscopic domain so that she could enrich training using microscopic images. And so the idea here was we have dermoscopic and macroscopic domain, and so we have both generators in both directions, and also we need two discriminators, one to distinguish real dermoscopic images and one to distinguish real from fake macroscopic images. So these are some examples of the results she obtained. These are really good examples because if you look, for example, from dermoscopic to transformed macro or fake macro, it really applies the properties that we associate with macroscopic images, like the visual glare. Here we have a clear notion on volume, on depth here as well with other colors. So it really did a good job in matching from one domain to the other. And finally, she had to compare some metrics on the segmentation, which was the final goal. And so we had a smaller data set, which is called DermoFit, of macroscopic images. And she also tried doing raw transfer learning from one domain to the other. And she saw that augmenting the data using the CycleGAN generated macroscopic images improved significantly the performance of the segmenter. Okay, so moving on to a different problem, meet iFunduscope. This is a prototype that we developed at Fraunhofer using our 3 groups. And so this is 3D printed at our facilities. You can connect a smartphone, and then you can get images from the iFundus. And so the idea was that this device could be affordable, portable, and used by non-experts. But when compared to those thousands of dollars tabletop big retinographers, this one still is lagging behind in image quality. And so one idea that we proposed to Beatriz Simões, that did her master thesis with us, and she will actually defend that thesis in a few weeks, was to perform an image, improve the quality of these images. And so she first had to do some dataset selection, pre-processing, where low quality images is input in the pipeline, and then with the help of a deep learning model, we would get high quality images as output. Okay, so just to show you a bit some examples of images that we work with. These are typical images of a data set related to diabetic retinopathy, which is a disease that affects differently the fundus that can be recorded with this type of imaging. And so here we have different degrees of the disease. And we can see, for example, from A to D, the worsening of some aspects in the image. And then we have another data set that had image quality annotations. And so we have annotations for good images, usable and rejectable images. And so we would, based on this, we would be able to evaluate a bit more the results of Beatriz's work. So just a note on pre-processing. We, of course, and if you are working with GANs or any other type of networks that handle imaging, there's always some pre-processing steps. In this case, we have to turn the aspect ratios in a uniform manner, as we show here below. We have to normalize the images. We have to resize it to a fixed size. So for those of you that work with this type of thing, you're already familiar with this. And so she designed a CycleGAN for this purpose. And so we can here see the 2 generators. And so here is multiplied. So this generator is the same, and these are the same. This is just the 2 possible paths. So from one, let me start here. From one low quality, we can transform into higher quality and then reconstruct again the bad quality. And the other way around, we can start with the higher quality, degrade the quality, and get back the original result, and with this corresponding discriminators. Okay, this should be familiar by now with the previous explanation. And okay, I have mentioned so far the ways to evaluate CycleGANs. And so the obvious way, and it's still practically it's still the best way to do this with images, is to judge them with human experts. In this case, unfortunately, we couldn't get expert validation for this work because they were not available at this time, as you may imagine. But it's still on the plans to get a panel of ophthalmologists to evaluate if the translated images would actually increase or improve the image quality. So we had a CycleGAN that was agnostic because there are different types of defects or artifacts present in the images. And so she built one CycleGAN that was agnostic to the type of defect. And we can see here some of the results. For example, here I selected 2 of them, which one of the defects is this clear aura around the image, which is successfully corrected, or underexposures that we can somehow correct. We can also see here some other examples that visually are improved. But then we also tried to build a CycleGAN that was defect specific. So we have a GAN for each type of defect. And this was also a tedious work, but an important work that Beatriz had to do, which was to separate the different types of defects and artifacts. And so here above, we see that aura around the image that is sufficiently corrected. And we saw visually that separating in these defect-specific GANs had more impact visually, but not so much in the other metrics. Here we see underexposure that it's corrected. In this type, it was even better than before. These are some spots in the image that somehow we can magic correct. And this type is some vessels that are illuminated when they shouldn't, and we also minimize this effect. Okay, so another way, a standard way for evaluating objectively the learning of a CycleGAN or GANs in general is using inception score or Frechet inception distance, but we did not use them in this work because this depends on, for example, ImageNet pre-training, which is based on animals, vehicles, and stuff like this, which is very different from retinal images, and so the scores would not be so significant. And so because we had that data set annotated with image quality, we trained an image quality evaluator with a good performance, and then we could assess the shift towards a better quality. So before image translation or improving the images, we get this confusion matrix. And the idea that we came to verify actually with the results is a shift here. For example, here in this cell, we see a shift to the left, and the left means from usable to good or reject to usable. And so we see a shift in the classification of quality. And so we have here another hint at how good the model is in improving quality. Of course, this isn't perfect because the classifier isn't perfect, but it gives you another idea on performance. Finally, and the other way to evaluate the impact is to assess how the transformation or the usage of this type of tools affects the performance of a diagnostic classifier. So Beatriz did this for diabetic retinopathy using efficient net B0, and we get similar results when filtering the images, like 73% of Cohen's kappa. However, she did find a statistical significant correlation between image quality and disease severity. And so what she found was that as the severity went up, the image quality went down. And so we can understand this because usually older people have more severe disease, and they tend to also have cataracts or other conditions in the eye that make the image a little worse in terms of quality and artifacts, or they can sit still in the acquisition, and so this degrades the quality. And what we did is we decreased this correlation. So even though the diagnosis results are similar, we decreased this correlation, and so it actually improves the confidence in the results. Then we also applied this for a glaucoma classifier, and we have yet to publish this soon, very, very soon. But using, and this was interesting because using for augmentation, both the improved images, but also the degraded ones, actually improves the classifier's performance. Okay, so this ends my presentation. I think we have a few minutes, right, Inish? So I think I can go ahead with the tutorial. Hi. Hello, just let me know how many.
Yeah, we are exactly on time. So if you want to continue, go ahead and we'll do the questions later.
5 minutes to go through the.
Okay.
Okay. Okay, I think you can see the screen, right? So the idea is that we cannot train a CycleGAN in this short time, but I found a tutorial in CycleGANs using TensorFlow 2.0, and here we are not moving away from horses and zebras. And so the idea, you can run this, because it's a Google Colab, you can run this, I will share the link also. And this actually uses TensorFlow examples Pix2Pix, because you can reuse the generator and discriminator from a Pix2Pix network to build a CycleGAN. And so here they load the data set, horses and zebras. I'm going through this. This is just pre-processing, random crops, normalizing, augmentation, simple augmentation. And here it loads and processes. This is just an example of the images, one horse and one zebra in the augmented version. In this case, okay, we have two generators and two discriminators. And so we get generator G and F. We load them from PixPix UNet generator. And we need also two discriminators. So we load them from PixPix discriminator. And so we can have a sample horse and generate a zebra, or a sample zebra and generate a horse, just to see how it starts in the beginning. So it's just gibberish, just random noise. Okay, and then we have the discriminator, which outputs not a single score for the whole image, but remember this is a patch GAN, and so we have a heat map of probabilities in each patch. Is it a real zebra or is it a real horse? Okay, just the definition of loss functions. So the main loss is binary cross entropy, that it's available in Keras, for example. And so the discriminator losses is the real loss, where you combine a matrix of ones with the real one, or a matrix of zeros with the generated one. And so the average of the discriminator is this one. And the generator loss is just simply the generator with ones, with the whole ones. And so we have also to include the cycle consistency loss. And so the cycle consistency, you have a real image and a cycled image. So cycled images, remember, it's generated and then reconstructed back. This is the definition of cycled. So this just defines this difference between the real image and the cycle. And then you have the identity loss, which is just the real image and the same images. So this difference should be as close as possible. This here we chose the optimizers. This is just to save some checkpoints. And then we have here generate images, so give you an input to a given model and show the example. And so now we can call this from a training step. Here it's a TensorFlow 2.0, but it's using explicitly the gradient tape. And I like this because you can more easily understand what's going on under the hood. And so you take a real X and you generate a fake Y, and you take a fake Y and you generate a cycle X, so the whole cycle. And you do this for a real Y as well. Real Y, fake X, cycled Y. Okay, so you can also try and use the generator from real X to expectedly generate the same X and real Y to the same Y for the identity loss. And then you provide this to the discriminator to get the heat map of probabilities of being real or not. And you pass the real ones and the fake ones. Calculate the loss for the generator, the GAN loss, and you sum the cycle loss. And then you sum also, you have the discriminator loss for each one. Then you calculate the gradients for each one, you apply the gradients for optimizing, and you run it as well. I put it here running a while ago, and so we are on epoch 18, but you can start to see that it's already applying some stripes. We have used some artifacts, but it's already, after 18 epochs, it's already starting to apply the zebra stripes to a horse. Okay, and then you could just generate using test sets. And I repeat, you can use this in every machine, because this is a Google collab, and I will share the link. So now I think I'm finished, so I'll stop sharing.
Hi.
Thank you.
Thank you so much, André, for your great presentation. So now we can go to some questions. My first question was your second example. And is the goal here to use again for filtering the data instead of augmenting the data set?
Okay, you're talking about the Retinal images, right?
Yes.
Okay, the initial idea is that after building this, we could use it as a standalone filter, that we would get low quality images and we get outputs of high quality images. And So it can be used as a filter.
But you want to enhance the images.
Yeah, but we can also use it for augmentation. And she actually tried, for example, a unit framework that actually the trade-off between reconstruction and generation was more easily visible. And so we can also use this for augmenting the data sets. And for glaucoma, we are seeing that using even the degraded images for augmentation improves the classification performance. But the initial idea, it was to use to build a filter, a retina image enhancer of sorts.
Okay, so the goal was to produce high quality images from low quality ones, right?
Yes.
Okay, great. Thank you. Another question is that similar to CNNs, is it common to perform data augmentation to the training data set before training GANs?
Yes, for every image-based model, and you see here in the example in the tutorial, they perform a simple augmentation because it also helps the network to become invariant to things that you want it to become invariant or equivariant. For example, the rotations and flips, even masking some portions of the image, it really can help the learning of that.
Okay, that's very interesting. And now we have a question from Ivo. He asks, how do you see GANs going forward? Seems like they are mostly used for image generation. Do you see the same potential for generating songs by mixing genres? Is that possible given the time dependency?
Yes, and actually they are doing this, and Google has big projects related to the arts, and includes music as well. It's called Magenta. And you, of course, because GANs are a high-level architecture, you can inside you can use convolutional networks, you can use LSTMs, new networks that come tomorrow. So the idea of this adversarial training still holds with different networks under the hood. And so you can, yes, you can mix text, you can generate, for example, one of the works that I find most interesting is giving images and providing captions, or giving a description. I want a blue bird sitting on a tree, and it generates an image, realistic images from that. And I guess for music, you can also combine genres. There's a really cool website of Google AI where you can do experiments, and one of them is not mixing musics, but it's mixing sounds, and you can make a trumpet mixed with a cat or a cow, and you can do all sorts of the things that they have GANs, and especially CycleGAN or friends behind it.
Okay, thank you, André, for sharing these examples. We'll take a look at it. I have another question. What are your thoughts on using GANs for medicine in underdeveloped countries? And I ask this because you said during the presentation that you could replace like a very expensive machine by a phone. And so this could make a huge difference in such countries.
Yes, and it's actually a concern of ours at Fraunhofer, is this decentralized healthcare. And so AI in general, not only GANs, can really help in achieving these goals, because smartphones are very powerful, and if you can leverage their power in applications like this one to replace, because even in Portugal, you don't need to go to underdeveloped countries, because in Portugal you have many of the regions in Portugal don't have enough dermatologists for screening, and skin cancer is one of the most prevalent in Portugal. And so we don't need to go that far. But for example, for the art fundoscope, one of our motivations was to apply it in underdeveloped countries, because you can ship a dozen of those portable eye fundoscope, or even if they have a 3D printer over there, they can print it closer to home, assemble it, and start using it. Of course, GANs help in improving the quality of the results, but I'm guessing technology and AI in general should be targeting this type of applications.
Yes, and related to this, are GANs always used in combination with other models? For example, are GANs mostly used for augmenting or enhancing the quality of your data set, and then you use another model that uses GANs outputs as inputs. Is this the normal flow?
Yes, usually it's like that, because if you're using, for our case, if you're using this to generate things to enrich a data set, then we could focus on the model. In our case, it was efficient net B0 for the actual classification, because the purpose is different. But your purpose could be actually generating things or translating or mixing musics. And so you don't need any other network. The GAN itself does the job. So it depends on the actual application. But for us, in classification problems or segmentation, the pipeline is usually like you said.
Okay, great. That was very clearing. And my last question is, what optimizer do you use for training GANs? And the typical question, how hard is it to find a good learning rate? And also, are these new models easier to train?
Yeah, I wish Katarina and Beatriz were here to talk about it, because they were the ones to suffer from this, because tuning GANs, learning GANs is still an art form where you have to tune. You have to look at, because the metrics are not so objective, and so you have to look at what's being output by the networks. But they are much easier to train than in 2015, when I first trained one to generate celebrity faces in the course, and it was really sensitive. And now it's much more easy to train. I think Fabiana also mentioned some tricks. The Wasserstein GAN over the vanilla GAN improved a lot on this. Then you have gradient penalties that you can use. Here we were using in the tutorial, they were using Adam. Even before this conversation, you were talking about a new optimizer that they say it's very good to train GANs. And so there are many smart people working on new research for stabilizing GAN training and providing new optimizers for this task.
Okay, thank you. Thank you for your explanation. And I guess we have two more questions. We still have some time. And Telmo asks, is it possible to use GANs to control GANs until perfection? How will it be possible to distinguish real from fake?
Okay, so we're talking about GANception, right?
Yes, yeah.
There's no technical limit on how you can control the GANs, and there's a lot of work on meta learning that uses neural networks to train neural networks. And so I never saw a GAN controlling a GAN until perfection. So, but the idea, some work are including, because one thing that it's hard to give to a machine is the human perception, but there are interesting research on this, on applying some loss functions that more closely matches our human perception of images, for example, or sounds or speech. And they're using stuff like this to improve on how to evaluate. And if the evaluation gets to the point that it's more objective, then I can believe that we can use other networks. I'm not sure if GANs, but other networks to fine-tune the GANs to make the result even better. And on the other hand, there are GANs that are specifically trained to distinguish real from fake, because most of you must have heard about deep fakes and putting Obama saying things and Trump and Putin. It's okay. Of course, it can be very dangerous, and there's a whole research line in just to concentrated on training GANs to distinguish and really good discriminators between real and fake. So even GAN research follows a GAN-like structure, where in the cat and mouse race.
Try to distinguish the real from fake.
As GANs get better in generating, so GANs should also get better in distinguishing.
Yes, okay. Thank you very much for your thoughts on this. And the last question is from Lucas. He asks, GANs are hard to train. How to get around that in a production context?
Yeah, in a production context, this is the same advice for every other type of network. You have to train you have to account for as most as you can for the different conditions that you expect to encounter in real world data. Because of course, if the distribution is different, for example, the horses and zebras, in the training data there were no riders, and then someone gives a photo of a rider, and okay, this is not supposed to happen. And I think one important topic is, of course, reliability and consistency of AI algorithms. And my personal belief is that AI should be treated almost like clinical trial. So you train things, and so you say my training data had these types of characteristics, and I won't expect that outside this world in production that the model behaves as I expect. And so if you define the conditions of training very well, then you are safe against someone saying, okay, it should do this and it doesn't. Okay, but I trained with this one. I know that my conditions are controlled, and it's very hard because even if you train a GAN sufficiently well for your known data distribution, when you get to production, it's a whole different story. And we actually didn't put this type of models in production yet, the GAN-based ones, but I'm assuming that we would have great challenges ahead.
Yes, and maybe something that can be done is to keep training the models so that they don't, so that they can learn from new examples and maybe new.
Incremental learning or online learning is very important when you put any AI system into production.
Okay, I guess that's it. Thank you again, André, for an excellent presentation, and thank you for answering all of our questions. And I'm just going to ask you to fill our feedback form, and if you're interested in doing a presentation with us, please fill in our speaker form. And once again, thank you, André. It was a pleasure to have you here.
Thank you. The pleasure was mine.
Yes, and we see you all next time. Thank you so much for coming. Bye-bye.
Bye-bye. Thank you.